Welcome to my presentation. At the beginning, I can tell you a little story because I actually was a research engineer of Mr. Hust that got this very nice award yesterday, and it was always a pleasure and fun working with him. I enjoyed that 6 years, and he always helped me to sharpen my ideas and my inventions. When I prepared my talk and I got the title Creating Freeways Ready for Autonomous Vehicles, I thought about the freeway authorities and the freeway owners. What could and would they really do to create such a freeway? And then I had to conclude that this would be a really short presentation because they would do nothing. Because they have completely other problems at the moment, at least in all countries that I know. Maintaining the existing infrastructure is the major problem, and not creating any new infrastructure for a system with unknown effects for the population and the drivers. So I came up with a subtitle: what would be the expectations of a freeway authority on an autonomous vehicle system? And I think that these expectations are driven by the experiences a freeway authority has with its own traffic management systems. So a fully automated vehicle system should, at least in their opinion, have the same effects and benefits as the systems they already have implemented. And freeway authorities think, and I think it's also partially true, that they already have a fully automated vehicle system, or at least a fully automated traffic management system, because it runs automatically. And I want to show you what in reality, on the example of a variable speed limit system, these systems have as effect, based on capacity and efficiency, traffic flow characteristics, and on safety. And you will see that the human being is doing a fantastic job when it comes up to the efficiency of a freeway. It does a better job than anyone else, but you will see that in a minute. And at the end of my presentation, I want to show you a little roadmap that demonstrates or shows how I think could be the path from now to a fully automated freeway system. And the main question is, does a system now increase the capacity or efficiency of a freeway? And previous studies assume that there's a gain in capacity up to 20%, and I call that the big myth about variable speed limit systems. How does such a system work at the moment? You can see a little chart here. We have stationary detectors on the road that measures flow and speed. We have a control algorithm, and we show on an overhead gantry the maximum allowed speed, and it's obligatory for everybody that sees it and drives under it. So it's 100% coverage. What we did, we analyzed tons of data, years of data of such a system, a variable speed limit system on a beltway surrounding Munich, the A99 freeway displayed here. And you can see the little boxes and in blue and in red, and these are the overhead gantries and the detectors that measures the traffic flow. And on these gantries, there's either displayed the speed, or there also can be warnings on the displays and signs for no truck passing or construction zones. When we analyze the effects of a traffic management system, we usually use speed contour maps, speed contour plots. That's a very common technique. And that's a speed contour plot of this freeway, and in traffic engineering, green is always good and red is always bad. And in green are high speeds and in red are low speeds. And you could clearly see that there are two bottlenecks that cause the congestion on this freeway. And the congestion forms downstream of the freeway. Here are the red areas with low speeds and congestion. What have been the signs for this congestion on the overhead gantries of the variable speed limit system? I just briefly display them here. You could see that we had lots of truck no passing signs, which are displayed in yellow, and we also had all different kinds of maximum speeds on that day. It is very difficult and time-consuming to go through all this data, and I just want to briefly summarize the major results. This is a zoom into the first congestion on that day, called bottleneck 1 here, and bottleneck 1, and we always identify a bottleneck if we have free flow traffic downstream of the bottleneck. This is on detector 140 here. It's always green. So, and if we have queues or jam upstream of the bottleneck, and this is on detector 130. So this is clearly the bottleneck of this freeway, and you could see here that this bottleneck and the reason for the jam, more or less, is this entrance and exit ramp. And the queue propagates upstream against the direction of traffic, displayed by this dashed arrow here. With a technique called transformed oblique curves of cumulative vehicle counts, we can then further trace the exact development of this congestion and see how many cars actually were parked on the freeway and what was their loss in travel time. And here the blue line separates from all the other lines at 7:47. So the queue arrives at this detector and the cumulative count goes up, while the other curves still stay together. This means that there are still free-flowing conditions downstream of the bottleneck. If we look at many days, we can see that there is a major difference if such a system operates or if it is taken off. And this is the really nice part of the data set that we have, that the freeway authority needed to repair the overhead gantries while we were still collecting traffic data. So we had data sets where there was no variable speed limit signs displayed, and we have data sets where the variable speed limits were in operation. When the variable speed limit is in operation, you could see that the main form of congestion, and I usually use 4 forms of congestion that I distinguish: a shock wave, which is just one wave of slow traffic, a stop-and-go traffic, more waves, more or less in parallel, but always with free-flowing conditions in between, so you have to decelerate and you have to accelerate. A wide jam, the big difference is there are no free-flow conditions anymore between the waves, and a mega jam, which is really huge in time and space. If such a system operates, you could see that almost every second jam that occurs is a wide jam. If a variable speed limit does not operate, the major form of congestion are stop-and-go waves. So there's a big difference in the form of congestion, and also for the driver, of course. This is a continuously 60 drive, while this is a drive 80, 20, 80, 20. And now it gets really interesting. When we look at capacity, so this is more or less the maximum flow that goes over the freeway, we can see that we have a reduction of flow when the system is on of 4%. So in comparison to the situation to free flow. If the system is switched off, we have in general higher volumes, but also the drop of capacity is lower. It's only 3%. And there's even a flow gain, an increase in traffic flow and efficiency, more or less, of 1% in the middle lane. So that's why I called it the myth of traffic, of variable speed limits. In fact, they do not do anything else than if there would be no system installed at all. We have the same capacity on the freeway, but we have different forms of congestion. We have a different distribution of flow across lanes. If such a system operates, we have an underutilization of the right lane, but the center and median lane, this is a 3-lane freeway, are used equally. If the system is switched off, we have still an underutilization of the right lane, but the median and right lane are unbalanced. Almost 40% of the vehicles drive on the median lane. This is the left lane. And if we look, there's just another calculation, if at passenger car equivalents, the flow in the right lane is higher, but it's still underutilized because this factor takes in consideration that we have more trucks on the right lane. If the variable speed limit is on, we have a shock velocity. This is the speed that that the jam propagates upstream of about 11 kilometers per hour, while if it's switched off, this same speed is 17 kilometers per hour, which means you need to brake harder if you enter the tail of congestion. And this, of course, is presumed a reduction in safety and a higher risk of crashes. Percentage trucks per lane, we had, as I showed, the sign that there's no truck overpassing. And this leads to the fact that 56% of all trucks are in the right lane. They still overtake. And some trucks can be observed in the center lane as well, but there are no trucks in the median lane. If we don't have a system on the freeway switched on, if it's off, we have a much higher percentage in the center lane, but we do almost also have no trucks in the median lane. What is now the result? What is, how is the system really functioning, and what do we need to do if we want to create such a system with autonomous vehicles? We have 2 detectors at the moment, stationary at 2 locations. We have a bottleneck in between, and we know that there's free flow downstream, a queue upstream. We measure capacity at the detector downstream, but we are blind more or less in between. We have no information about that. And detectors can be pretty far apart. We are talking about distances of 2 to 5 kilometers, so we don't have any knowledge about that, what happens in between. And we developed the ski lift analogy to illustrate how a variable speed limit works. And you could see the scenario when this speed limit system is on. So what happens? We have a very harmonized queue. It almost happens on a real ski lift, by the way. And we have pretty large distances between the vehicles, but we do not have much lane changes. And where we measure capacity, every chair of the ski lift is full, and that's the value that we obtain for capacity. If we switch the system off, it becomes more like a real ski lift, I would say, but it also doesn't have a variable speed limit system, a ski lift. The queue is really chaotic. The lane changes occur also immediately upstream of the bottleneck, and you could observe aggressiveness between the drivers and when you look at the lane changes. But when you look at the point where we measure capacity, we still, the people are still able to pack a person on every chair that is available. Only the queue is different. So, what is the result? The results confirm safety-related aspects of the VSL system, so they produce safety. We also had a look into accidents, by the way, this also confirmed that. But the systems do not increase capacity, which people still tell. Efficiency might nevertheless result from possibly avoided accidents. So if you avoid an accident, the system is still fully efficient, and the truck overpassing sign seems to be very effective. So if a freeway authority thinks about an autonomous vehicle system, it has safety expectations, and these expectations are correct, but they have wrong expectations on increasing capacity and efficiency. And you could see that people, even if we do not have any system in operation, can produce the same efficiency on a freeway than with or without. So what could be the path from a variable speed limit system to a fully automated freeway? This is how it was today, and you saw it already. By the way, I'm not at slide 129. And what could be the next step? Freeway authorities by now do not use any floating car data to control such systems. And also, we only have vehicle signs of maximum allowed speeds by now out of video cameras, more or less, out of the car. So there's a video camera looking at signs or overhead gantries, but there's nothing else. And the first thing is that freeway authorities take the floating car data. And I have a little chart here that shows these are actually the data that control the variable speed limit system. These are data from TomTom devices, and these are data from mobile phones. They all look the same, obviously, because it's the same freeway and the same jam. But you could more or less substitute a stationary system by now if you use mobile phone data. So you could have the same results. Of course, you need a highly loaded freeway, but only on highly loaded freeways we usually install variable speed limit systems. This would lead to scenario 2, where a freeway authority doesn't need any stationary detectors anymore. It could fully rely on floating vehicle information. Of course, it would still need an overhead gantry because it's obligatory, as I said. And only if we have a 100% penetration with equipment and systems, we would be able to get rid of the overhead gantries as well. Because then we would be sure, at least we would think we are sure, that everybody receives the actual maximum speed limit that is set on this path of the freeway. I hope I fulfilled your expectations on an interesting presentation, and I'm happy to take your questions, I think, in the workshop. Thank you very much.